Hi all. The video you're about to watch was originally recorded on the 20th of February. I thought I would edit it and post on YouTube during the next weekend. No one could imagine that just a few days later, Russia would start a full-on war with Ukraine, and that over the course of the next 72 days, the Russian army would inflict so much loss and suffering upon innocent people. This broke my heart, and I can only wish that this war ends soon and that people start rebuilding what was lost. For me personally, it took a while to get past the initial shock and a while more to start doing some of the normal things. Life's not back to normal, but perhaps certain things can be. And this video is one of these things. I started doing a series on how to implement a compiler for a functional language early this year. So far, I've covered term reduction and tree walking interpreters. But the real fun starts with the bytecode. And in this video, I will flesh out the basic structure of the bytecode and the virtual machine to execute this bytecode. And in the follow-up videos, we'll proceed with handling of arithmetic, environments, and function application and function abstraction. So everything. Well, anyhow, hope you'll enjoy it. Let's talk about compilation. Say we have a program that is initially in the form of source code. In case of Fang, it may look something like this. Let x equals 7 in x plus 42. To compile this program, we take this initial representation and we transform it into some other form, which is usually just a sequence of instructions. So we have instruction 1, instruction n. When these instructions can be understood and executed by your real computer, we have native compilation and a native executable. On the other hand, we could make these instructions target not the real machine, but an imaginary, or in other words, a virtual machine. This indirection allows us to compile once and then run everywhere. That's the promise that Java makes, that C# makes, and many other languages. So when we say bytecode compilation, we usually mean this. We generate instructions for a virtual machine, and this virtual machine is stack-based. Let's talk a bit more about this. So, as we have established, we need a virtual machine and the bytecode. The bytecode is a sequence of instructions. And the virtual machine, the stack-based virtual machine, has at least the stack. That's where all the intermediate values go. And that's where, that's what the bytecode instructions operate on. And a program counter, that's basically like a pointer to the next instruction in the bytecode. Now let's imagine we have an instruction called immediate int with one argument. the integer. Let's say immediate int 5. When the virtual machine executes this instruction, it just pushes 5 onto the stack. Let's add another one here. Immediate int 7. When we execute it, we put 7 on the stack. And let's say we have another instruction, integer add, that doesn't have any arguments. But what it does is it pops its like 2 of its arguments from the stack, it adds them, and then pushes the result back onto the stack. So when this instruction executes, we get something like this. So a stack with just 12 on top. Now this is pretty straightforward, and if we had only the arithmetic in the programming language, that would not be very interesting. But luckily Fang has lambdas and closures, which adds a lot more to the bytecode and the implementation of the virtual machine. So figuring this like ways to compile lambdas, closures, and execute all this stuff, that's gonna be fun. Bytecode generation and bytecode execution require quite a bit more setup. So to keep this video under hopefully 1 hour, I will fast forward certain parts and will just explain what the code does after the code has been written. Cool, so let's start with some basic types and interfaces. First of all, we need the type of the instruction, and let's populate it with the halt instruction that will cause the virtual machine just to stop. Then let's define the type bytecode, and I mentioned that bytecode is basically a sequence of instructions, so we can make it an array of instructions. These may not be the best representation, and just generally note that all the types defined here will not be final. They may change as I flesh out more and more of the code, but for now let's go with the array of instructions. Then we will need the module called VM, and inside this module we will define the type VM. Since virtual machines are inherently imperative things, it's, I think, appropriate to make it an object that accepts bytecode as a constructor argument. Now the VM will need a couple methods. So let's define the method execute that will just execute the bytecode. Let's also define the method current value that would just return the top of the stack if there is any value in the stack. I guess the question is what kind of type it will return. We'll get to this later. And well, I mean, we don't have the stack as well, so let's work on those. So we need a stack of something. And the question of what this something can be, I mean, it's not a simple one. Different virtual machines support different types of values on the stack. Some support only boxed, some support boxed and unboxed values. We will define the type value, which will be like a boxed representation of everything, because working with boxed values is easier than with mixed box and unboxed. So we will have an integer value, and let's add require qualified. All right, so we have defined the basic skeleton for the VM module. So we have the type of the value that the virtual machine will have on the stack. We have defined the virtual machine object and some basic methods like execute and current value. We are missing a code pointer, so let's add these as well. Let's make it an int right now. This again can be changed in the future if needed. Cool. So now let's work on the bytecode generation. So I guess we need a function called generate bytecode that takes an expression and returns bytecode. Now let's define BytecodeBuilder. This will be a helper class that will allow us to gradually generate all these instructions, and then when we have processed all the nodes of our AST, we will be able to just call build on this builder and have our bytecode in the end. So let's define member. It will take an expression, and well, for now it will not do anything. Let's also define the method build that would just return the bytecode. Let's say for now it just returns an empty array. So then the generate bytecode method would look like this. Now let's work on the generate method. So this method takes an expression as an input. And given that our expression type is recursive, generate will probably also be a recursive function that would match on the expression and just emit the appropriate instructions. Let's start with matching on the expression. And if we go to the language, first, probably the easiest is to match on literals. Let's define another helper function. So here we would need to emit instruction, and I guess now is the time to define some extra instructions. So we already have halt. Let's add integer constant. Oh, and as a side note, I really dig this require qualified access attribute. So in Haskell there is qualified import, but here the control is sort of inversed because the API author can decide whether a certain type needs to be accessed with a fully qualified name or not. So I think that's an interesting design decision for sure. I find it using quite often. All right, so we have the int const instruction. So let's submit it. Good. So now I think the next milestone, the next good milestone is to implement kind of the arithmetic. So this means the literals, which we have we? Yeah, so we have integers and units. So we need to implement the literal, the handling for the unit type as well. And also the arithmetic and comparison and all these built-in operations on integers. So let's do this. So this is maybe a little bit controversial, like how to handle the unit type or the unit value. Let's just emit 0, because why not? We can always fix this later on since we are in control. All right, so let's proceed with the arithmetic. So this arithmetic is actually a bunch of binary operators, and also comparison is a bunch of binary operators. So let's perhaps define a new type of instruction called int binary op. And let's define this type as well. So we could separate arithmetic operations from comparison operations, but to simplify things, let's just dump them under this type and see how it goes. So now we have all the necessary pieces to implement the generation of instructions for arithmetic operations. And the interesting part is that we will already see this recursive aspect of bytecode generation, even on this simple example. So what we will need to do to implement the arithmetic, we will need to generate the bytecode for operand A. When this bytecode will be executed, the result will be on top of the stack. So when we generate the bytecode for operand B, so here the stack would be value A. Here the stack would be value A, value B. So value B is on top, value A is below it. And then we need to emit the instruction. So this instruction will be int binary up from arithmetic fn let's do it like this. Then the instruction would be int binary up of operator type Oops. So to recap, to generate the code for the binary arithmetic operation, we generate the code for the first operand, then for the second operand, and then we emit the instruction, whether it's addition, subtraction, multiplication, or division. Now it should be pretty easy to handle the comparison. And finally, let's add the unary operators. We need to add the new type of the instruction here. So at this point, we have all the bits and pieces that cover basic arithmetic. So let's perhaps kind of flesh out this function. All right, so this is nice and tidy. And now we can also implement this function as well. So we take this array, bytecode buffer. Good. Now let's switch gears a bit and go to the VM and try to implement the necessary functionality to make the virtual machine evaluate, this bytecode with arithmetic operations. Okay, so here we need to implement a run loop of the virtual machine. So what we do, we take a look at our code pointer. If there are any other instructions that need to be implemented, we try to do it. So first of all, we take the instruction out of our bytecode. Then we increment the code pointer to the next instruction. And finally, we match the instruction. So if it's halt, then I guess we could do it in a couple ways. We could either advance the code pointer to make it exit on the next iteration of the while loop, or we could set the flag. Let's go with the flag. All right, so now if we see int const instruction, we need to push the value onto the stack. Good. Now let's deal with the binary operators or operations. If we go back to this bytecode generation, we see that the second argument is on top, then it's the first argument. So we have arg2 . Now these arguments are values, and we need to ensure that these are actually integers. So let's define some helper functions that would fail if we're not getting the type that we need. This is really similar to what we have done in the tree interpreter. Okay, so let's add another type of value here. Let's call it black hole. First of all, is just to make this branch sensical in this context, but we will also need this type of value later on, similarly to what we have had in the tree interpreter. Amazing. So now we have two integer values, or we fail if the values are not integers. That's fine. Now, our result depends on the type of the binary operation that we have. Now that we have the result of the operation, we need to push it back onto the stack. So with unary operation, it's also very straightforward. We pop its argument from the stack, and then we negate it because that's the only unary operation we have, and then we push it back onto the stack. It actually seems that at this point we have everything that we need. So let's define a function. Maybe let's call it, well, let's call it eval. It takes an expression and it returns a value. So first of all, we convert the expression to the bytecode. Then we create the virtual machine. Then we execute. I know that getting a value from an option is frowned upon, but I mean, this is the example, so let's just go wild. Perfect. Let's go back and try to incorporate our bytecode interpreter into the demo app. Come on. All right, so if we have done everything correctly, then the first example should actually work. So the plain arithmetic. Let's see. And voila, we actually have both the tree-based interpreter and the bytecode interpreter producing the same result. And maybe just for fun, let's go to the bytecode, put a breakpoint somewhere here, and just, you know, see what gets generated, how things work. Just do it step by step to get a better feel of you know, this bytecode interpretation stuff. So here we have the bytecode with 5 instructions. We have 2, 3, 4, multiplication and addition. So multiplication is applied to 3 and 4, and then the addition is applied to this result and 2. And this corresponds, I think, correctly. Yep, so 3 and 4 multiplication, 2 plus result. Great. So let's just step in and see. We get the instruction, it's int const, we advance the code pointer, push it onto the stack. Cool. Let's do the couple more steps. We have 3 and 2. And now we have 4. And the next instruction is multiplication. We pop 2 values, multiply them, push back onto the stack. 12. Addition, pop 2 values, add them up, push back onto the stack. And that's it. So in the end, we have the VM with integer of 14 on top of the stack. Perfect. And just like that, in only 42 different steps, we have implemented the basic structure of the bytecode generator and the virtual machine. Yeah, it's quite a bit more involved than the tree walking interpreter, But I guess when you need this extra performance, it's actually worth it. Anyhow, next up, we will add support for variables and handling of the environment, and after that, support for function application and abstraction. I hope this was helpful. You'll have a good time, and thanks for watching. Peace.